Hi everyone, welcome to the Data Idol Summer School and welcome back to our community who have been following us for the past 5 years. Also, welcome to any of you who are new in our community and new to the Data Science Festival. I'm Charlotte and I'm the Recruitment Operation Manager at Data Idols. The Summer School is a new pilot programme in partnership with the Data Science Festival. It will run live for 3 months so you can learn in real time and pick up new skills from the comfort of your very own home. These sessions are designed at an introductory level, ideal for any of you who are transitioning into data or looking to start out in your career as well. Please use the Slack channel if you are watching the session live to chat with other attendees, and the link will be in the chat soon. You can use the channel Data Idol Summer School for any event-related questions, comments, or feedback. We'd also like to thank all of our partners who have made this event a success, and for the 400+ hours it's taken for our team to make this summer school a reality. All of our sessions are pre-recorded and can be watched back at a later date from September. So on September the 1st, we will be emailing you a link to watch the sessions back, which will be free to watch at any time. So if you miss anything or want to learn at your own pace, then they'll be there for you. Today, we will hear from Partha Dey from Perlego, giving a session on an introduction to data engineering and best practices. We'd like to thank you very much for supporting the Data Science Festival in partnership with Data Idols, and we really hope that you enjoy the session today.
Hi, welcome to Introduction to Data Engineering. We'll be covering various topics today. See this video as a Data Engineering 101, covering various different frameworks, tools, and technologies. So, let's see what we're covering today. First, we'll define kind of what data engineering is because, it's a very new field, there's lots of overlaps. We'll see key differences between data engineering and other roles. We'll look at business use cases. We'll look at the challenges that data engineers face with data being everywhere. We'll look at how a model, for example, a machine learning model, is trained and the life cycle of what goes on and how a data engineer contributes to that. We'll look at cloud computing and architecting for scale, and we'll look at further learning. So one thing I would like to say before we start is even in introduction level videos in other video series, I have a practical section where I'm programming something to show you how to create a script or tool or something like that. But in this video, I'm not going to do that. The reason being is just covering the tools on a high level, I think will be enough for you to carry on learning. If I start diving into practical examples and actually start building out data infrastructure, there's a very real chance I'll lose you very quickly. This isn't an advanced level video, so since it's a more introduction level video, we'll just be covering things on a high level, and hopefully after that things will start to make a bit more sense for you so you can start tackling more advanced topics in other video series or other material online. Okay, so let's get going. Let me introduce myself first of all. I'm Partha Dey, Infrastructure Manager at Perlego, and I manage the Cloud Infrastructure and DevOps Engineering team at Perlego. What is Perlego? Well, it's an online digital library. Join Perlego today to get access to over 650,000 non-fiction and academic titles, and start today with a 14-day free trial. You can access Perlego anytime on our website or on our mobile apps. Okay, so first things first. What is data engineering? Well, it involves the design, development, and management of data infrastructure and architecture, which collects, centralizes, cleans, and pre-processes data and makes it readily available for data scientists to then go and analyze. Now, as you can hopefully see, and you will see throughout this video, there is a lot of overlap between what data scientists do and what data engineers do. So I would like to just touch on a quick example just to explain this. So imagine I have an algorithmic trading company who uses algorithms to trade on the stock market, and they want to find relationships between news events and stock price fluctuations of technology companies. So as you can imagine, if I have news about a certain company, it's very bad news, then you can imagine the stock going down. And this company wants to automate that process so they want to build a system that can automatically, read news and then understand what's going on, then predict stock prices going up or down based on that. So data engineers in this case will build the infrastructure and data stores, which brings all of the disparate data sources together, cleans them and centralizes them, ready for a data scientist to go and analyze. Now, the important thing here is the data sources to start off with, because data is everywhere, and obviously a data scientist shouldn't have to waste time getting all that data before they even start working on it. So that's what data engineers do. And then data scientists then use that pre-processed data that the data engineers has procured for them to gain insight by applying techniques or algorithms, and is then able to work with stakeholders in a company to come to a solution for the company for the future. So as you can see, data engineers play a really crucial role for a company, and it makes them aware and able to take advantage of data that's already out there. Now, it's important to stress data really drives businesses. And in my previous example, it was a very in-depth example where the company is trading based off of data and automating the entire process. But it doesn't need to be as in-depth. For example, a company may need to simply find out exactly how its users are using the product, and imagine that a company wants a breakdown of exactly who uses what and how they use it. So a business needs to be aware of its surroundings so it can better plan for the future. Any business needs to do that. And insights about its surroundings is gained and predicted by data scientists. Now, data scientists need data to work with, and data engineers are there to build the architecture infrastructure to help collect this data. Now, what you'll generally see is that smaller companies tend to have people who do a lot of everything. So they will build the infrastructure, build the architecture, train their machine learning models, they do everything. But in bigger companies, there is a need for individuals to specialize in a certain thing. So in a bigger company, you might have a dedicated data engineer, dedicated data scientist, dedicated machine learning engineers, dedicated analysts, and so on. But in smaller companies, it's very common for you to do multiple things, which kind of stretches over multiple job roles in bigger companies. Let's go through some of the challenges that data engineers overcome. The first thing, data sources are everywhere, and the lack of unification makes analysis difficult and cumbersome. Imagine I have dozens of data sources in multiple databases, on the internet, and so on and so forth. Imagine trying to gain insight from that data, which is what, after all, a data scientist is trying to do, without trying to bring all that data into one place. And this is why data engineers are so critical. Data scientists simply can't do their job if data engineers don't bring the data nicely packaged up for them. Next up, automation is key. Repetitive data collection and cleansing activities should be automated to save time and reduce human error. Companies should really automate as much as they can to make use of their resources. And what you'll see is that companies, when they start out, may do things quite manually, but in bigger companies, we're dealing with lots and lots and lots of data. That sort of thing doesn't scale. So automation is really key. Knowing how to build architecture that is elastic and can grow with the company and is quite automated, very automated if possible, is really, really a good thing. Next thing is just a principle: garbage in equals garbage out. So I always say this phrase to many people, and what does that mean? Well, imagine I have a machine learning model that tries to predict outcomes. For example, I'll give you an example. I used the trading example earlier, but suppose I have a transport company and they want to predict the increase in passengers over the next few years. Well, you train a machine learning model to try and predict that based off of previous data. If you give that model something bad to train it on, i.e. data that is terrible, noisy, and has missing values and so on, then it can make the model really unpredictable. The predictions that it will make will be inaccurate, and it will just be garbage in the end. So garbage data in equals kind of garbage model at the other end. And very much if you imagine you're trying to teach a child, if you can't teach that child with proper resources, then the child won't learn very well. And treat a machine learning model just like that. And the last point is that whatever you build needs to be able to scale. Companies deal with vast amounts of data, and data engineers need to build solutions that scale elastically with business demand. Simply put, elastically just means that when there is not much data or there's not much data processing happening, infrastructure should be quite small and it shouldn't cost very much. But when the time comes that I am dealing with huge amounts of data and I need a lot of data processing, then the data infrastructure should be able to scale perfectly with that, and the cost should go up proportionally in line with the amount of data that you're collecting and you're processing. Now, let's go over what is good data. In the third point from before, I've said that garbage in equals garbage out. So how do we make sure that we don't feed our machine learning models or any model that we're trying to train with rubbish data? Well, good data is processed raw data that can be used to effectively train a machine learning model in this case. So good data has the following characteristics. Data sets are large, feature-rich, do not have null fields or inconsistent missing values. They're representative of the distribution of outcomes, and there's fair sampling. So let's go through each of these bullet points. If my data set is large, then it makes sure that my model has plenty of information to learn from and infer from. The next bullet point is feature-rich. By feature-rich, we're basically saying that the data has enough information to give a model enough context to be able to infer something useful. Now let's go through a good and bad example of this. In my previous example, I've said, right, a transport company trying to work out passenger footfall going forward. Good information would be things like, hey, the date and time which passengers enter and exit a station, the season, for example. So you might expect in summer there might be slightly less people using the service, and in the winter more people are using the service because people are on holiday in the summer. That sort of information is useful. Providing random information like what color clothes they're wearing, their favorite lunchtime item, their gender or something like that, that's not useful. And all you're doing is just making a very messy data set, and then the model will start picking up random inferences that are not intended, and it will give you a very bad prediction at the end. The next is does not have null fields, missing inconsistent values. So let me give you an example. Suppose I have in my passenger footfall example in a station, if I have lots of blanks, let's say I'm giving it minute by minute information, but suddenly there's a 1 hour gap or a 30-minute gap, that doesn't help the model. The model likes nice consistent data sets with no missing values. So if we can try and remove them before we train a model, then that's a very good thing to do. We'll wrap up the representative distribution of outcomes and fair sampling in one example. So suppose again in the passenger footfall example, I'm training my model. Let's say I give it only 1 day of data, and that 1 day happens to be, there's a football match going on. So as you can imagine, the amount of footfall in the passengers is going to be huge. And is that representative of a day's activity? Not really. In a day you might expect, in the peak hours in the morning and evening, you might have a lot of people, might be a bit quieter around lunchtime and so on. But if you train a model just on match day data, then the model will think, okay, there's always going to be a load of people coming in at all hours all the time. So that's why we need to give data which is representative of outcomes, and it's fairly sampled, so the model has good context going in before trying to learn something. If you give it data which is biased or skewed, then the predictions it will come out with in the future will also be biased and skewed. Now let's go through the model lifecycle. Now, as you can see, I'm really basing this around a machine learning model that we're trying to train, and we're trying to give it good data. And for the rest of this video, we're going to try and stick to this sort of scenario just to make things a little simpler. This is a model lifecycle in general. So let's say a scenario wants to develop a machine learning model to predict future stock price fluctuations. There's identifying the data sources, getting the data, cleaning the data, preparing the data, training the model, measuring how effective the model is, deploying it to production, and then measuring how useful it is in production in a live environment. Generally, as a data engineer, you'll be dealing with these 4 things: identifying your data sources, getting data, cleaning the data, and preparing the data. Machine learning engineers and data scientists will generally take on the train and measure, which takes a long time, and then the deploy and measure stage at the end. In bigger, more established companies, you might have a dedicated DevOps engineering team to kind of deploy and measure how good a model is, but it's expected, maybe even in small companies, that a data engineer might end up deploying and measuring the outcome too. So again, depending on the company, these roles can overlap quite a bit. Okay, so let's now stick to this structure. We're going to look at data sources, how we can get data, how we can clean and then prepare data. Okay, our first data source are APIs. API stands for Application Programming Interface, and it allows for us to easily expose data and be able to consume it in a really easy way. Here's an example. Suppose I want to find out the weather information about a certain state or city. I'm using the Open Weather Map API here, and as you can see, I'm going to api.openweathermap.org. I am querying the weather for a certain city name, and the app ID is just an authentication key that I pass it. And here's the response from the API. So it's told me, in this case, the weather in Mountain View in California. It's telling me the min and max temperature, the pressure, humidity, and so on. And as you can imagine, an application developer can now easily put that into his application. So like a weather application on your phone, for example, uses this in the background to be able to present you with information. Now, as a data engineer, you'll work with APIs a lot to gather data and to actually enrich existing data sources. So you might have some data from your company, but you might want to use some API to add more value to the data, some more information to the data. As a data engineer, you'll be working with a lot of APIs, and they can be used to gather data and enrich existing data sources. Suppose I have a platform and it uses Stripe payments as its payment provider. Well, let's say I want to find out information about my users. Well, I've got a list of users from my users database, but let's say I want to go ahead and find out which users are, paying for their subscriptions or paying for services and so on. Then what I can do is I can use the user IDs in my database, go to Stripe payments and pick up information about that user. How does Stripe payments expose their data? Well, they use an API. Next up are SQL databases or SQL databases. And SQL databases store relational data, and it's very much what you're used to when you imagine tables of data. So imagine I have a Excel table here. This is very much how you can imagine a SQL database table. And in this case, I've got some employees here. So I've got John Smith, Henry Wickenshire, Joseph Broadfront, and Katie Jenkins, their job positions and their locations. You can use the SQL querying language to query the data. So I've got an example here. Select all, the asterisk just means all, from employees where the location is London. And as you can expect, the result is just John Smith, marketing executive in London. Now, one thing to note is one of the database services that you can use is Amazon AWS's RDS. AWS is Amazon Web Services, and we'll be covering more cloud products later on, but RDS stands for Relational Database Services, and it's one of the products that AWS have to allow you to create databases, in this case SQL databases. The next data source are NoSQL databases. So as you can imagine, it's the kind of the opposite of SQL databases. And NoSQL databases store data in a non-relational way, and it forgoes the traditional tabular form that SQL adopts, and there is no need to define a schema beforehand. So in my previous example, my table has very, very fixed columns of ID, name, job, location. Suppose I wanted to add another field. Well, I'd need to add another column and then add in all the new information. And it can be a pain if your data form is not known. So in NoSQL, we forgo any schema at all, right? So the data is stored as objects. And you know what, it's really useful. Suppose I have a product catalog, right? So I've got two products here. In the top one, I've got a 4-piece garden furniture set, price $3.99, and the second one is a Nissan GTR RC race car, remote control toy, 1 in 32 scale, $14.99. Now, as you can imagine, the information pertaining to a flat pack furniture is different to a toy. So as you can see, I've got the assembly field in my furniture set, and in the second one I've got information about batteries. Now, would it make sense to have a giant database table and then include battery information about flat pack furniture? Of course not. So as you can see, different products need different fields, and instead of having fields, we call them attributes. It's a very flexible way of storing data, and generally the way you can think of it is rows of data are replaced with objects, and columns, instead of having fixed columns, we have attributes. In this case, in my furniture one, I have the product ID attribute, product name, assembly, price, and currency attributes. And in the second one, I have product ID, product name, batteries, battery quantity, price, and currency. Now, there are various services to allow you to create NoSQL databases. So, for example, AWS's DynamoDB is one, or you can use something open source like MongoDB. Next up are time series databases. So time series databases are used specifically for data to do with time valued data key pairs. So imagine stock prices, for example. A time series database may store minute by minute information about various stock prices, and obviously you can measure how it fluctuates based on that data. Weather information, again, I might have a hourly weather service, and I will store information on an hour by hour basis, let's say temperatures of a certain city. Now, it's useful to have time series databases because they're optimized for time data, and some of the services that you can use from AWS, you have TimeStream, and if you want to use something open source, you can also use InfluxDB. I've also written a blog post actually about Amazon TimeStream on Medium. Go ahead and read it. It gives you a 101 on how to get started with Amazon TimeStream. Next up is object storage. Object storage refers to things like images, videos, text files, and an example is Amazon's S3, which is part, under the AWS umbrella. Well, in an S3 bucket, you'd store again things like images, videos, text files. You wouldn't use it to load an operating system or anything like that. Think of it as like a giant USB thumb drive in the sky, which stores static objects like this. Next up are data lakes. So you're gonna hear and see data lakes, data warehousing everywhere when you learn about data science and data engineering. So let's cover what they are on a high level. So data lakes store raw data that may not be ready to use for analysis or training a model, and there are many different sources and formats. And data lakes use a flat structure to store data, and data can be stored very flexibly. And one thing to note is data is processed upon export. So a lot of the time a company will have loads of data and it doesn't actually know if it's useful or not, but we know it's useful enough that we want to keep it. So this is where data lakes come in. I just see it as a dump. You dump information in there. You don't really know how it's going to be used, but it might be used one day. And the day that it is used, the day we export it, we then process that data to make it useful. Let's say I want to put it into a SQL database. I can export that data, process it, and make sure that the data in my table is all correct, and the data scientist can make use of it. The being able to process that data is where data engineers come in. Being able to set up the infrastructure to have a data lake in the first place is where data engineer would come in. An example might be IoT, which stands for Internet of Things sensor devices. I'll give you a random example. Suppose I have a smart fridge and a company wants to measure the temperature of the fridge every minute, and there are various other things I can measure from the fridge, like the humidity, the amount of power it's drawing, and so on. Suppose I don't really know what to do with the information now, but I do want to keep it because I might want to use it in the future. The fridge manufacturer will store that data in the cloud and data lake, and when it is ready to use that data for some actual use, it will go ahead and process it accordingly. An example of a service that allows you to create data lake is AWS's Lake Formation. Next up, data warehouses. So it's a central information repository that stores processed information ready for querying and analysis, and data is processed upon import. So data lakes, data warehouses, very similar names, quite different use cases. So in a data warehouse, the information is nice, clean, processed, ready to go, and it can be used by a data scientist or data analyst to do some sort of work. In a data lake, it's just a dump. I'm just putting things in there, and there might be a use for it in the future. Data warehouses, on the other hand, there is a use for the data straight away, and it's processed. And the data is processed as you're putting it into the database. You don't put in, unclean data into there. So data is therefore processed upon you importing the data into a data warehouse. An example might be, let's say I have an advertising company and they're storing, clickstream data, like, when you click on adverts and stuff, they're storing clickstream data and they want to organize it by user identifier. So, for example, a data scientist might want to work out which adverts you're more likely to click on in the future. They can use your user ID and then group things based on kind of what you clicked on. And as you can imagine, that sort of information has to be nice and clean, because if I have just random information about all users, about everything they click, it's very messy. That information would go in a data lake, but in a data warehouse, I would have it nice and clean so I can actually gain insight from it straight away. A very popular database warehouse service is from AWS and is called Redshift. Now, there is an open source tool you can use as well called Apache Hive. Again, we'll cover this a bit later on. Next up, we have to look at how we can get data into our infrastructure. So the way we can do that is with data streaming. Now, here's the thing. You can use it like a little script, a Python script, to get data into our infrastructure, but let's say I want to build something more robust, something that works in real time. That's where I would think about data streaming. It's the idea of capturing data that is continuously generated by different sources in real time and sending it to a target upon where transformations are carried out and makes the data ready for analysis or querying. So, an example might be streaming real-time weather data to continuously train a model to predict the weather in the next hour. Let's dive a little deeper into this example. Suppose my raw weather data comes back with lots of extra information, like air pressure. And suppose I only really just care about the temperature and the humidity to be able to predict the weather. Feeding the model unnecessary information won't do it any favors. You'll train it on data which is messy, and again, you're going away from good data set principles here. So the data engineering infrastructure not only should pull in the data but clean it, ready to train the model properly. Some examples of data streaming services include Apache Kafka, which is open source, or AWS's Kinesis family of products. So we've now looked at how we got the data. Let's look at how we can clean and prepare it. What do we mean by that? Well, it's the idea of transforming the data prior to processing and analysis. So an example might be removing anomalous sensor data and removing duplicates and enriching the data with an API. So earlier when I mentioned my smart fridge, suppose on a certain fridge, I don't know, there's something wrong with the power supply on the fridge and it's drawing way too much power, right? Well, in that case, if I then feed a system with that anomalous data, then it will kind of mess up the model. So I can basically, in my data engineering infrastructure, set up thresholds to say, right, this is anomalous data, don't include it in. And all of this should happen in a very automated way. Because if you, let's say, have millions of fridges over the world, doing that manually will become quite annoying. There are various services that help to do this, and there's a lot of overlap between service A to service B, but some services that can help you do it are Apache Spark, which is open source, or AWS's Glue, which is a managed ETL or extract, transform, and load service. Again, we'll look into these later, but I'm just putting them here just as example services. Next, let's look at cloud computing. As a data engineer, your life will be in the cloud. Because you'll be dealing with huge amounts of data, you can't possibly afford to do that on your local machine because your laptop or desktop will literally heat up and explode with the amount of data that you'll be throwing at it. Cloud computing allows you to provision compute resources on an on-demand basis, and you pay for exactly what you need when you need it. And we've mentioned AWS already, but some of the other cloud providers out there are Microsoft's Azure and Google's GCP, or Google's Cloud Platform. So not only do they provide like the raw service for you to actually run your data engineering tasks, they provide entire suites of products and services dedicated to data collection, processing, and cleansing, and there's even machine learning and AI products which then use the data to gain some sort of insight. Okay, so now we're going to talk about architecting for scale. Whatever solution we build has to scale for the amount of data we need to ingest and process, and it needs to be able to scale elastically. So there are a large number of services and products available to achieve the 4 stages we outlined before. The 4 stages being identifying our data sources, getting our data, cleaning and preparing our data. So out of the tools, some are open source and some are managed and provided by cloud providers such as AWS. To allow us to build something to scale from day one, we'll look at products from a cloud provider, in this case AWS, but before we do so, let's understand some of the open source tools that are already out there. The first open source tool we're going to talk about is Hadoop from Apache. Hadoop isn't one product as such, it's a collection of open source tools and utilities that uses a network of computers to solve problems with very large datasets. Hadoop splits our large datasets and files into blocks and distributes them across nodes in a cluster, and data is all processed in parallel. And there is a storage part, which is HDFS, which is the Hadoop distributed file system, and a processing part, which is MapReduce. Now, Hadoop is really important, and you'll see in a lot of other tutorials as well. Obviously, we can't get into the deep dive into how to implement it, but I would like to give you some idea into how it works, because the other utilities and tools we'll discuss will depend and run on top of Hadoop. The first thing we'll talk about is the Hadoop distributed file system, or HDFS. Hadoop clusters basically have nodes, master and worker nodes, and as you can imagine, worker nodes kind of do all the work of processing your data, and master nodes kind of choreograph all of it. And these master and worker nodes orchestrate and execute various jobs across the entire Hadoop distributed file system. Each node, worker node for example, has its own disk space, memory bandwidth, and processing activities, and data is split into blocks which are stored in HDFS. And HDFS assumes a worst case scenario. It stores 3 copies of each dataset throughout the cluster. The master node keeps on track of all of this. So imagine a huge computer. I'm splitting up into little nodes. I have worker nodes which kind of look after the I have master nodes which look after the worker nodes, and it takes a large amount of data, splits them up into little portions, and it kind of processes all of them in parallel, which, as you can imagine, really speeds up the rate at which you can process and transform data. Even more on Hadoop. So Hadoop needs to coordinate these nodes exactly. So if the nodes become out of sync, you can imagine things will start to go wrong quite quickly. Things on this scale, so if you imagine terabytes, petabytes of data even, things on that scale can't go wrong. If they do, then you're in a world of mess dealing with so much data. So MapReduce, which is a framework used to process a lot of data in parallel on large clusters, it was used to manage resources, on my nodes, and process all that data. But more recently we use Yarn. Yarn stands for Yet Another Resource Negotiator, and it basically takes MapReduce's resource management and scheduling capabilities and data processing capabilities and splits them all up. So that means that MapReduce can just solely focus on data processing, and the resource management and scheduling, that's handled by Yarn. Even more on Hadoop. I promise we're nearly done. So as you can see from my chart on the right, we've talked about the distributed file system at the bottom in yellow. We've spoken about Yarn. Now we're going to talk about the processing framework layer. And it includes frameworks that analyze and process datasets. Structured and unstructured data are mapped, shuffled, sorted, merged, and reduced into bite-sized data blocks. These actions, by the way, of mapping, shuffling, sorting, merging, reducing, is handled by MapReduce. Operations are spread across multiple nodes. Those things such as Apache Spark and Tez helps MapReduce and use the Hadoop distributed file system to the fullest to take full advantage of it. And lastly, right at the top, we've got the API. So as the big data industry kind of grows, the need to access the data in the processing layer becomes more and more varied. So we can use tools like Apache Hive, which is an open source data warehouse, to create data warehouses, and Apache Pig to create programs that run on top of Hadoop. And as time goes on, I'm sure there'll be more tools that access data in the processing framework layer via the API. Okay, so now that we know what Hadoop is, we can now run frameworks and tools on top of it. So the first one is Hive. Hive is an open source data warehouse that can be used on top of Hadoop, and it provides a SQL-like interface, and it can query databases and systems that are integrated with Hadoop. So I've got an example here from a blog post on dellane.co.uk, and in this case I'm writing a SQL query, select title, release year from the Mario Kafka table, where sales millions is greater than 25, and as you can see, it's come back with the results as you would expect from a standard SQL query. Next up is Spark. Spark is a distributed processing system, and it's used for big data workloads utilizing in-memory caching and optimized query execution for fast analytical queries against data of literally any size. a thing to focus on is in-memory caching. So that allows Spark to run extremely quickly and in a very performant manner, which means you can run queries and other executions at huge scale. It supports code reuse across multiple workloads, and you can achieve things like batch processing, interactive queries, real-time analytics, machine learning, graph processing, and even more. As the days goes on, Spark becomes more and more feature-rich. It does a lot of the heavy lifting to process and transform data into a usable form that, let's say, a data scientist might need. Next up is Kafka. It's a distributed event streaming platform for data pipelines, streaming analytics, and data ingestion. A use case for Kafka is, for example, imagine I have user activity tracking on my website. Actually, the original use for Kafka was for this. I want to stream that data into a database or a data lake, for example. I would use Kafka for this. And I can also use it for things like operational monitoring data and log aggregation too. Next up is Airflow. So in a complex workflow where you have data being processed in multiple different ways, how do you make sure that it's maintainable, testable, and it fosters a collaborative development environment? In a company, it's not going to be one person working on a workflow. You're going to have entire teams working on it. So how do you manage it in a nice structured way? Well, Airflow is used to author workflows, and here's an example here on the right, and it models the workflows as directed acyclic graphs, or DAGs, of tasks. You might be wondering though, what's a DAG? It's a good question. So DAGs are directed acyclic graphs, and let's break this down. So a graph mathematically is just a structure which totals a set of objects, and some of the pairs of objects are related. On the right hand side here, I have a very simple graph. I have 3 points and 3 lines. The lines are known as edges, and the blue dots, the points, are known as vertices. Now, if I go a bit deeper and look at the directed word, a directed graph has edges with directions. So as you can see, if I start out at L1, I can either go to X or I can go to Y. Now, going further with an example, we actually use directed graphs in everyday life. This is, for example, a family tree. A family tree is an example of a directed graph, and as you can see, it flows downwards from John and Mary down into their children and down into their children. Let me give you an example of a cyclic graph. As you can see, if I start at X, I can go to Y, which directs me to A, which directs me to X, which directs me to Y. It's cyclic. There's a cycle going on here, and you're being directed in that cycle. As you can imagine, if you're a computer system trying to execute some logic, this is not a very good idea, because you're going to just be going around and around and around and around in an infinite circle, and your program won't end up executing. This is an example of an acyclic, non-cyclic rather, graph. So if I start at L1, I can either go to Y or I can go to X. So put it all together, it's a directed acyclic graph. And if you now look at the Apache Airflow example I have here, the very simple one, this is a graph. So run me 0, run me 1, run me 2 runs first, which goes off to run after loop, and run after loop, and also run this terminate at run this last. Okay, so hopefully that gives an idea what DAGs are, and if you read about it online, you'll be able to kind of navigate it a bit easier now. Let's talk about cloud computing, and let's talk about AWS. So AWS has a range of products to help us with data engineering. So the first one we're going to talk about is AWS Glue. AWS Glue is a fully managed serverless ETL service, and ETL stands for extract, transform, and load. And it makes it simple and cost effective to categorize the data, clean it, enrich it, and move it reliably between various data sources and data streams. So very simply, the ETL process or ETL pipelines, they get data from a source, change its form, transform it. Maybe I want to remove some columns, unnecessary columns, remove some of the null fields or empty fields and so on, and then enrich. Maybe I want to enrich the data. Maybe I want to call an API and add some extra information to this data set, and then it sends it to its target data source. So after I've transformed it, I might want to send it to let's say a data warehouse or database, for example. Next up, let's talk about Kinesis. Kinesis allows you to collect, process, and analyze streaming data to allow you to get timely insights. and it's able to process streaming data at any scale. And it's actually a family of products which can be broken down into video streams, data firehose, and data analytics. Let's take a look at each one now. First one I have is Kinesis Video Streams. What is it? So it allows you to stream video from connected devices to AWS for analytics, machine learning, for playback, and for other processing. An example of where you might want to use Kinesis video streams is, let's say I have a cloud-enabled CCTV system, a CCTV camera. I can connect up to the Kinesis video stream, and it ingests, stores, encrypts the videos, and indexes the videos for real-time analytics. I can now send that off. For example, imagine in the CCTV, I want to track. Let's say I want to count all the people in a certain CCTV stream. For example, let's say I want to count the number of passengers in a station, and I want to do it just using the CCTV. Well, Kinesis Video Stream can take that CCTV footage. It can send it off to Amazon SageMaker, which is a machine learning platform within AWS, or maybe I can send it off to Amazon Rekognition, which is a computer vision platform in AWS. I can also send it to other things such as TensorFlow, or even just to play it back, maybe in like a dashboard where you want to view your previous CCTV data. Next up, we have Kinesis Data Streams. What is it? Well, it's a scalable and durable real-time data streaming service. So in this example here, I've got my input going into Kinesis Data Streams, which ingests and stores the data for processing, and then you can send it off to Kinesis Data Analytics, Apache Spark on EMR, an Amazon EC2 instance, or even an AWS Lambda function. Now the cool thing is you can now visualize all that data using a tool such as Amazon QuickSight, Microsoft Power BI, or Tableau. If you haven't used a BI tool or business intelligence tool, then here's an example. Here's Power BI, and as you can see, we have all of our data in nice visualizations, which allows you to present lots of data in a very easy to grasp way, which is, as you can imagine, extremely important in presentations and meetings and so on. Next up, we have Kinesis Data Firehose. What is it? Well, it allows you to capture, transform, and deliver streaming data into data lakes, data stores, and analytics services. In my mind, it's like a removal man with its huge van, which can move data from building to building, or from service to service, or from data store to data store. And I can use Firehose to take data from my source and send it up to, let's say, an S3 bucket, into Amazon Redshift or Elasticsearch, so I can search all that data really easily. And then, as before, I can output the data into a BI tool such as QuickSight, Power BI, etc. Lastly, we have Kinesis Data Analytics. What it allows you to do is process and analyze streaming data, and the really nice thing is you can build Java and Scala based applications using open source libraries based on Apache Flink. Apache Flink, by the way, is an open source stream processing and batch processing framework. So that is the 4 Kinesis products that make up the Kinesis family. Next up, we have Amazon Redshift. It's a fully managed petabyte scale data warehouse service that makes it simple and cost effective to efficiently analyze all your data using your existing business intelligence or BI tools. The really nice thing about it is you have all of this data, but it's exposed via a SQL endpoint, just like any other database, for example. The difference with Redshift and open source tools such as Apache Hive is that Amazon manage everything for you, configuring and provisioning the infrastructure for the data warehouse, making sure it's secure, making sure it's updated. It does all of that for you, and when you need to scale it, it's also really easy to do so. So that's why managed services go a long way into helping businesses scale really, really easily from day one. Next up, we have AWS Data Pipeline. It's a managed service that allows you to automate the movement and transformation of data, and it allows you to design data-driven workloads, and you can basically chain tasks together, so previous tasks can be used to trigger successive tasks. So as we mentioned before, automation is really key, and Data Pipeline really helps with this. So you can have multiple tasks, chain them all together, and when this task finishes, the next one starts, the next one starts, and so on. There's very little human intervention, if any, required, and it makes life a lot easier when you're dealing with huge data-driven workloads. Next up, we have AWS Lake Formation. It allows you to set up a secure data lake quickly and usually within just a couple of days. Next up we have EMR, which is Elastic MapReduce. So we touched on what MapReduce is earlier. Amazon have a product called Elastic MapReduce, or EMR, and it easily runs. It easily allows you to run Hadoop and other frameworks such as Spark and Hive, and the key being it's on managed AWS infrastructure, and it makes it easy to set up, operate, and scale your big data environments, and by automating time-consuming things like provisioning infrastructure, tuning clusters, updating them. AWS does all that for you. We can now start wrapping up and looking at some example architectures using AWS products. Now, I can totally understand being exposed to so many different tools and services and products can be super overwhelming, and sometimes, because these services overlap so much, it's very difficult to know when to use what. The aim of this video was to give you a high-level overview of the different tools that are out there, and now hopefully after going through these example architectures, you can go ahead, carry on learning, experimenting, and seeing how you can put all of these products into use in the real world. The first example architecture that we're going to go through is how to query an S3 data lake. Now, going through this architecture, we have an S3 bucket here, we have a Glue data crawler, a Glue data catalog. This then goes to Athena at the top, EMR, which we've covered, AWS EMR to run Hadoop, and then we have Amazon Redshift at the bottom, right? We've touched on the bottom two. Let's quickly understand what Athena is. Athena is a query service, and it makes it really easy to analyze data in an S3 bucket. Now, S3 isn't a database, it's an object storage service, but Athena still allows you to query that S3 bucket with SQL as if it is a database. So as you can imagine, it's a very powerful service. And lastly, on the right hand side, we have just a BI or business intelligence tool. I've picked Amazon QuickSight here. Okay, so let's understand how this works. We have our S3 bucket with kind of raw data, and we have our Glue crawler here. The crawler connects to the data store, in this case an S3 bucket, and it progresses through a prioritized list of classifiers to extract the schema of the data and other statistics. It's basically trying to work out the order and the patterns within the S3 bucket. After it does so, it populates the Glue data catalog, which is this one here. And as you can imagine, a catalog is literally, it gives you a list and orders all the data using an index. And it provides all the metadata that the Glue crawler has been able to pick up. Crawlers can run periodically to detect the availability of new data, so as and when your bucket is being updated, it can pick it up. Let's say you run the crawler on an hourly basis, for example. And it can pick up on changes to the existing data, including if you change the table definition. Crawlers automatically add new tables, new partitions to existing tables, and new versions of table definitions. And you can even customize Glue crawlers to classify your own file types if they are non-standard, for example. Talking more about the Glue data catalog, it's a central repository to store structural and metadata for all of your data assets which are in your S3 bucket. For a data set, you can store its table definition, physical location, you can add business relevant attributes, as well as track how this data has changed over time. The Glue data catalog is Apache Hive Metastore compatible. So if you are running Hive Metastore, and what is it? Well, it does the same sort of thing as AWS Glue. It can serve as a drop-in replacement for your big data applications running on Amazon EMR. The Glue data catalog integrates really nicely with Athena, EMR, and Redshift Spectrum. It's what you'd expect from a managed AWS service. Everything just works nicely with each other straight out of the box. Lastly, we have a BI tool at the end. We have, in this case, Amazon QuickSight, and it allows you to build visualizations, perform analysis, and quickly get business insights from your data. So that is how we can put these services together to be able to query an S3 data lake and then see the results on a BI tool such as QuickSight. Lastly, we have the architecture for a system that can gauge social media sentiment. So let's say I have a platform like Twitter. I can go ahead and analyze the tweets and then gauge what people feel about a certain person, topic, organization, or whatever. And I can do it in a very automated way. So let's go through the system. We have an EC2 instance. In this case, I have a C5 type EC2 instance, and it's in an auto-scaling group. And the autoscaling group will make sure that if I have loads of tweets needing to be processed, I can just spin up multiple EC2 instances to be able to deal with that load. The next step, I want to take my Kinesis data firehose stream and it loads it into an S3 bucket. I'm loading it into a directory within the S3 bucket, which is just like an unprocessed directory. It's got a file structure just like you'd have on your computer, for example. After data has been put into my unprocessed directory within my S3 bucket, it can then trigger an AWS Lambda function. Lambda is a serverless compute platform, and basically it works off of triggers. When this happens, execute this code, etc. So in this case, what I can program it to do is when my Kinesis data firehose puts an object into the unprocessed bucket, like let's say a tweet for example, it can then trigger the Lambda function, which can then work in tandem with other AWS services, for example Amazon Translate and Comprehend. Translate, as you can imagine, translates the tweet into English if you want, or other language, and then Comprehend then detects things such as entities and sentiment, and it uses natural language processing or NLP to do so. Next up, I have a couple of other firehoses. So a second Kinesis firehose delivery stream loads the translated tweets and sentiment values into the S3 bucket into these two new directories. So what I can do, for example, is I can post the named entities. So for example, let's say a certain tweet talks about Amazon, Jeff Bezos, Blue Origin, for example, right? What it can do is say, right, for this certain tweet, Comprehend has given me all this information and then about the entities in that tweet, and I can put it into the named entities directory within this bucket. And then let's say I've got the sentiment about that tweet, I can then put that into the sentiment bucket, and I'm delivering it all from the Lambda function via my Kinesis data firehose. So now that we've got all that information, we now need to be able to kind of query it and view it as necessary. So I can do that in a few ways. I can first I can send it off to Athena, and Athena of course allows you to query an S3 bucket using SQL queries, and I can display that on QuickSight to be able to visualize all that information nicely. I can also send that information to a Glue data catalog, and then as you can imagine from the previous example where I was using a Glue data catalog, you can do even further processing. For example, you might send it to Elastic MapReduce to run some queries on Hadoop, run some processing on Hadoop using frameworks such as Spark, for example. So that is a system to analyze social media sentiment. I hope I haven't lost you too much, but it's just an example of how you can use all these tools and services to create really, really powerful automated data engineering platforms. So that's about it. Let's look at what's next. Carry on learning. Perlego is a great place to get started. So we've touched on a high level about different architectures, tools and services and so on, but Perlego has lots of books on data engineering. There's more than 650,000 titles with loads of books on data engineering, and then there are also books about machine learning and artificial intelligence. So after you've got all of that data, you can then load it into core models and do whatever you want, really. There are books for beginners, intermediate and advanced topics are also covered, and these books are usually really expensive, so for a low monthly price you can access all of them on Perlego using our web e-reader or our mobile app. So what have we covered today? We've covered what data engineering is, an introduction to it. We've covered the kind of the overlaps it has with data science roles. We've looked at the key differences between data science roles and data engineering roles. We've looked at the business use case. In our case, it was the algorithmic trading company. We've looked at the challenges that data engineers face with data being everywhere, and we need to be able to automate it, clean our data, and so on. We've looked at a model lifecycle, a machine learning model in this case, and seeing the importance of being able to get, clean, and pre-process our data. We've looked at cloud computing, and we've looked at how to architect for scale using open source products, using Hadoop and other frameworks, and using AWS products too. And we've looked at more learning on Perlego using books. And we've covered further learning that you can do on Perlego. If you search for data engineering, you'll find loads of books on our platform. So that's about it for today. Thank you so much for watching. Feel free to add me on LinkedIn using this QR code. I'll be happy to answer any of your data engineering questions. Have a great day.